Hello everyone and greetings from New Zealand. I'm H.Biggs from NIWA and today I'll be talking to you about the Droneflow project, a stereoscopic camera system that we developed, an aerial tracer particle distribution system and more. So that's enough from me. I'll disappear from view and we'll get on with the presentation. Let's start with the slide showing the idea behind the Droneflow project. Essentially, we have an upstream drone that drops biodegradable tracer particles into a channel if there are a lack of natural traces or not sufficient density of natural traces, which then drift downstream to be imaged by another drone, either carrying a single camera in the case of narrow channels where ground control points or fixed reference points are visible, or a stereoscopic camera. Now, there are a number of advantages of using a stereoscopic camera system compared to a single camera. By using a stereoscopic camera system that's properly calibrated with synchronous images from either camera means that the location of objects in space can be resolved in 3 dimensions, which means that we can actually solve for depth of field. This generates the location of the points in camera coordinates in the camera's frame of reference. If this information is then coupled with RTK GPS for the origin of the camera system and then an inertial measurement unit for the orientation of the camera system, then points can be solved for in real-world coordinates. The practical advantage of this is that it allows for aerial image velocimetry in much wider channels without any fixed reference point. So usually with single camera aerial image velocimetry, reference ground control points are needed on the banks, and it's suitable for narrow channels where there are fixed reference points so the banks aren't moving. But the idea of using a stereoscopic camera system with RTK GPS and an IMU is that it should allow for measurement in much larger rivers. So for example, flooded rivers that may be up to 1 kilometre wide, where there's nothing but moving water that's visible underneath the drone. This is the stereoscopic camera system that we developed. Let's take the top off and have a look at what's inside it. So it consists of 2 global shutter RGB machine vision cameras, an Intel Nuke i7 mini computer. These are GPS antennas, and this is a battery. If we flip it over and have a look on what's on the underside, there is a power distribution board, an inertial measurement unit in the middle, and this is the GPS module here. With it all packaged up, we added some cooling fans at the front because it's getting a bit warm. There is a 3D printed chassis that it's all attached to. Here's the battery, and we also added a PWM connection which can be plugged directly into the M600 drone so that we can trigger it from the remote controller unit. The stereoscopic camera system is calibrated with a checkerboard calibration target in MATLAB, and it took us a little bit of time to develop the control algorithms for the cameras to get them synchronous, and we ended up adding an external trigger. And once the cameras are perfectly synchronous, you can see we can capture a bird in mid-flight with its wings fluttering, or some little windmills that are rapidly spinning, and they're perfectly synchronous in both camera images. Here's the stereoscopic camera system flying on a DJI M600 drone, and another shot of it when we were doing some initial testing in the Ashley River. And here it is up in the sky out at the Rangitata River. Next, let's talk about tracer particles. Tracer particles are needed if there's a lack of natural traces, such as in low flows, or maybe a lack of surface features. We've tested quite a wide range of tracer particle types, everything from wood chips, wood shavings, breakfast cereals, plain and coloured ones, and even types of foams. The best we found were wood shavings, and these were supplied by a company called Kiwi Wood Shavings, and they're cheap, lightweight, biodegradable. They work well in most rivers. We did have some problems though in shallow braided rivers with sun glint and surface waves. The issue in these situations is that the sun glint is brighter than the tracer particles, which makes them very hard to distinguish. And we found that dyeing the tracer particles red solves this problem. And we found this mulch dye that's used for dyeing faded bark chips, sort of a bright red color that people use for some reason. And this is non-toxic and safe for the environment, people and pets, which makes it pretty ideal for environmental applications. Once we have the red tracer particles visible in imagery, thresholding in HSV color space is simple to then extract only the tracer particles, and that's one advantage of using RGB machine vision cameras rather than just monochrome ones. This imagery can then be auto-rectified, a region of interest can be defined, thresholding then occurs, and this the image frames within the region of interest can then be exported as binary TIFF images, for example, which can then be fed through FUDA LSPIV or LSPIV performed in MATLAB or similar, generating distributions of mean surface velocities. The next part of the project was development of a tracer particle distribution system that would fly under an M600 drone. This is the first prototype version. It was a quick mock-up which had twin rotating screw augers. We had some problems with product bridging across that. So the next version, which was the lightweight version, had 3 screw augers in the bottom. Here it is being made out of fiberglass, and we had 3D printed section in the bottom with the 3 aluminium screw augers. And here is the final version, which is filled with tracer particles and has attachment brackets for going on the drone. It's controlled by a motor, which is actually a drone motor. There's a reduction gearbox, a speed controller, and a PWM cable that comes in to control the feed rate. And on our remote control unit that we use for flying the drone, we've got a rotary switch at the back that we use for changing the feed rate out of it. And it also fits nicely in a big box that we have for transporting out to the field. The tracer particle distribution system can be easily filled out in the field, and here's the field technician Hamish Sutton, who's one of the other drone pilots at NIWA, filling up the system before a flight. And here he is also down in the Tekapo Canal when we were down there doing some work recently, flying the system. And here it is again in the Rangitata. Here are some videos of the tracer particle distribution system in action. Here it is in the Rangitata River. And here it is in the Tekapo Canal, launching and flying upstream to start a mission. And this is a top-down view of the tracer particle distribution system. You can see it dropping tracer particles, which then drift downstream in plumes to be imaged by the downstream drone. And here's another video. This is from the perspective of the downstream drone. and you can see the tracer particles coming downstream here. Another important part of the project were development and use of rainproof drones for flood gauging. Consumer-grade drones such as the DJI M210, suitable for small single-camera payloads. However, to carry larger payloads, such as the stereoscopic camera or tracer particle distribution system, we partnered with Aerial Limited to develop a waterproof skyjib drone, which can achieve a 35-minute flight time with a 5-kilo payload and fly in quite strong winds of up to around 60 kilometers per hour. This is a video from Aerial when they were doing the waterproof testing on one of the original skyjib variants, and they then improved the waterproofing further for the skyjib that they provided for us. And that skyjib drone has recently arrived, so we got that this month. So the flood gauging is an upcoming part of the project. Another important part of the project has been work on surface alpha. So this is needed for LSPRV and STRV. There's uncertainty about the best approach to follow, the effects of wind, and ideally we need predictive equations where the inputs are derived from remote sensing data. So to address this, we've been working on deriving predictive equations for alpha, so that's the work that Graham's been doing, and also looking at some site-specific calibration methods. We've recently completed large fieldwork campaigns featuring velocity profiles and complementary wind measurements, and there's a advice document that we're working on, which will be released in June, on the accuracy of various different alpha methods and recommendations. Measurements for this part of the project have been completed around New Zealand, and the most detailed measurement set occurred in the Tekapo Canal, which was recently completed, and I'll give you an overview of that now. This is the Tekapo Canal site. It's a long, straight section of channel with discharges ranging between around 50 to 100 cumecs. In the middle of the channel, we deployed two up-looking acoustic Doppler velocity profilers. On the true right bank, we had a climate station. On the true left bank, we had a large wind tower that we partnered with Scion to develop, and so that had 3 Campbell Scientific sonic anemometers. The tower was 5 meters tall, and we wanted to record high frequency data there to resolve shear stress on the water surface from wind velocity profiles and turbulence. And also an ADCP, which we use for both bathymetry and validation of the discharge measurements from Genesis Energy, the hydropower company that operates this section of canal. Next steps in the project. There's a huge amount of data analysis and write-up that's underway and still to do. I've got the advice report that's coming out in June. Flood gauging in the rain is another thing that's on our list for upcoming. We'll continue with software development and working on a number of techniques for remote sensing bathymetry that we'll carry on with, and continue physical habitat mapping, and the project finishes in 2022, and we'll also release a software toolbox then. That's it. So many thanks to MB and NIWA, collaborators at regional councils, collaborators in Japan at the Hydro Technology Institute developing Hydro STRV. And if anyone has any questions or they'd like to collaborate, please just get in touch with me via email, and yep, it'd be great to hear from you. Have a great rest of your conference. Cheers. Bye.